Page 22. This is introduction to exercise 5.4 on sum, difference, and product of functions. Now the idea is all we're focusing on is ones that look like this. Okay? F plus g, f minus g, and f dot g. Alright? If we let f and g be two functions with intersecting domains, key being intersecting domains, then for all values of x in the intersection, the algebraic combinations are defined by the following rules. I've just filled it in for you. Okay? F plus g just means f of x plus g of x. Right? You might see it as literally just f plus g without the x, as in you might just see that. It means the same thing. Okay? Same thing with f minus g. Very straightforward. The product is f of x times g of x. Please don't get that mixed up, with composite functions. We'll do that next. Okay? But it's just the multiplication of. In some circumstances, you'll be asked to graph a function, or like a product of a function, or a sum or a difference of a product of a function. Sum and difference is quite straightforward. It does take a lot of thinking, but it's pretty straightforward. Right. I'm going to get you to write down two general rules for us. Okay? Now, in this paragraph, essentially what it's saying is this: the domain of f plus g equals to the domain of f intersecting with the domain of g. That's not new probability notation, is it? No? Okay. So the domain of our sum function, or our difference function, is where they are intersecting. The range is to be determined from the transformation of the domain by the combined function. So once you've got this new combined function, different from composite function, you then figure out, okay, well, the minimum is this value, the largest value is this value. Let's see where it gets cut off by the new domain, okay? Don't just refer back to the original function. The other rule I'd like you to write down is this. When f of x equals 0, f plus g equals g of x. This is not an all-encompassing rule, but it's a pretty general rule. Pretty much if we're adding two functions together, and one of them equals to 0, at that point where f of x equals 0, it's just going to equal to g of x. And again, we see those quote-unquote anchor points. If I know that my f of x is 0 at some stage, I might, for example, present to you two graphs and you have to add them together. If I know one of the functions is going to be y equals 0 or f of x equals 0 at some stage, I can just put a point as to where g of x is, for example. And of course, the same thing would apply for differences. Okay? It's something that makes more sense as you apply it. Very quickly, I'm just going to go through an example of finding f plus g, f minus g, and f g. We don't do quotient. I've put the formula there. If you're curious, but it's not part of the study design, don't stress. So let's focus on f plus g first. So with f plus g, all we do is we add our functions. In this case, it's x minus 1 squared plus 3 minus x. I had a question earlier when I was looking at holiday homework. What is reasonable simplification? What is required simplification? If an examiner looks at the question and it is a reasonable one, so for example, it's a simple fraction like 15 over 5, right? Or if it's a basic simplification of brackets, right? Whatever it is, if it's something that you should be able to do without a calculator, you need to do it. That is the assumption, yeah.
What page is this?
Page 22.
I don't have page 22.
New booklet is up here. I'll give it to you in a second. So, we've got the basic simplification. In this case, I am assuming this is what you need to do, right? You must simplify this. So I'm going to expand both of them, or one of them rather. We get x squared minus 2x plus 1 plus 3 minus x, which would simplify into x squared minus 3x plus 4. What is the domain of my f of x? What can x be? Any real value. Thank you very much. X is an element of any real value. Now you can write it two ways, just in case you've forgotten from last year. You can either write it as x is an element of all real values, or you can write, that's not an x. Alright, we'll do x here, and then negative infinity, and positive infinity. Okay, you could also do your interval notation as well, that's up to you. That is not going away. Let's move on to f minus g. Same principle. We go f minus g, which equals to bracket x minus 1 squared minus, I'm going to put in brackets as well, don't forget that, which expands to x squared minus 2x plus 1 minus 3 plus x, which we know simplifies to x squared minus x minus 2. So that is a assumed reasonable simplification. You should do that in assessment. What is the domain, what is the intersecting domain of my function? 3 minus x, could that be any x value? Yeah. So again, x is an element of all real values. This isn't a great example for intersecting domains, but you get the principle. Finally, fg, pretty straightforward. I'm going to multiply them instead. X minus 1 squared minus, times 3 minus x. That expands out to x squared minus 2x plus 1 multiplied by 3 minus x. In which case, we'd expand it. I'm assuming we're okay with expanding brackets that have, that have 3 terms. Lovely. So that gives us negative x cubed plus 5x squared minus 7x plus 3, again, where x is an element of all real values. If you want to find the range, you then take this new, consider this new domain. In this case, there is all-encompassing intersecting domain, so it's fine. But if, for example, our function is defined by a domain of 0 to 5 now, you have to find your range between those x values of 0 to 5. Not to say your y values need to be between 0 and 5, but you need to consider your function. Your new function only exists between 0 and 5 for x values. That trips up a lot of people. Any questions? Okay.